Welcome. In this video, I want to take a closer look at alcohols and the common reactions that they tend to undergo. So the general formula for an alcohol is CnH2n plus 1 OH. And remember, this makes sense because they're an alkane that's had one hydrogen group bumped off and replaced by the hydroxyl group. So the OH or the hydroxyl group is the functional group, which is a hydrogen bond, so it's going to make an alcohol very polar. And so alcohols are going to be more soluble in water than alkanes, plus they're going to be less volatile with a higher boiling point, and they're going to tend to be more dense with that oxygen in there. Alcohols can be used as fuels. They can be burned directly with oxygen, just like hydrocarbons, and they'll produce water and carbon dioxide and release a lot of energy, just like hydrocarbons or alkanes. But they burn cleaner than alkanes, which is a big part of the reason why ethanol is added to gasoline. And in Minnesota, all gasoline has ethanol added to it. So ethanol blended gas is cheaper, but it does decrease your gas mileage. So it's pretty much a trade-off. The cost is about the same to the car owner, but it's better for the environment. As the size of an alcohol increases, the amount of heat released will also increase because you'll form more CO2 molecules. So if you look at the two reactions below, there's methanol burning where 2 moles of methanol will form 2 moles of CO2 and release about 726 kilojoules of energy per mole. But if you take 2 moles of pentanol, it will make 10 moles of CO2. And just like it produces 5 times as much carbon dioxide, it produces nearly 5 times as much energy at 3,331 kilojoules per mole. So methanol has been viewed as a potential fuel replacement for fossil fuels. They're using it in hydrogen cell cars, natural gas cars, etc. And it can be synthesized by reducing CO2 and CO. So we could have an endless supply of methanol theoretically. Alcohols can also undergo incomplete combustion and produce CO just like hydrocarbons can, but that isn't real common with alcohols. Some fun facts about alcohol. These are things I'm not expecting that IB is going to expect you to know for the test, but just to kind of help you get a bigger picture of alcohols. Ethanol is the alcohol group that we safely consume. At least in moderation, it's considered a safe substance. So, of course, this is a huge industry, but that also then brings problems like people driving when they're impaired. So the tests for blood alcohol levels actually rely on a redox reaction with dichromate to see how much OH is in your system. The other way they can do it is with infrared spectroscopy. Because ethanol alcohol is abused by people, but we also use it in a lot of our industrial cleaners like Lysol. Anything that's a disinfectant very likely has ethanol in it. You may see the term denatured. And what that means is that they actually add a toxin to the ethanol to make it unsafe for human consumption. And hopefully at your age, you think it is just unbelievable that somebody would drink Lysol to get their buzz on. But chronic alcoholics will indeed drink anything to consume that ethanol. And so that's why it is denatured to prevent that from happening. Alcohols can be oxidized to carboxylic acids like acetic acid or vinegar, which is what happens if wine is left exposed to air. Once you open a bottle of wine, even if you try and use one of those fancy wine savers where you draw as much of the air out, there's going to be oxygen exposed to that wine and the alcohol in the wine. And over time, in a week or so, that bottle of wine is going to oxidize into carboxylic acid, notably acetic acid, and then really isn't considered to be very good at that point. So we can burn alcohols for fuel, the complete combustion, where the whole alcohol molecule gets converted to CO2 and H2O. But we can also selectively oxidize alcohols. And what I mean by that is we can use an oxidizing agent to oxidize only the carbon atom where the OH group is. So only that carbon atom is going to pick up any oxygen. The rest of the backbone and the rest of the molecule is going to remain intact or remain the same. So this allows us to produce other organic compounds, aldehydes, carboxylic acids, and ketones. And the most commonly used oxidizing agent for this to happen is acidified potassium dichromate 6, where it reduces the orange chromate 6 ion to the green chromate 3. And commonly we just show it with the oxygen in brackets to show we're using oxygen for the oxidizing agent. and we don't write out the whole potassium dichromate atom. But it's important that you realize that the reagent that's being used to facilitate these reactions is an acidified oxidizing agent. So then the oxidation will produce these three different potential products, and the type of product you get depends on whether it's primary, secondary, or tertiary. So you should know what product can be produced from each class of alcohol. So we'll look at the primary first. On the reaction here, I have ethanol, the primary, shown as a primary alcohol, which is the only option for ethanol with just 2 carbons. And if you add this acidified oxygen or dichromate ion with heat, it will remove 2 of the hydrogens from the alcohol. So it's going to remove 1 from the hydroxyl group. So let me just show this here. So this hydrogen will be removed, and 1 of these will be removed, leaving you with CHO, or if we drew that out, it would be carbon, double bonded to an oxygen, bonded to 1 hydrogen, and then with the CH3 group still attached. So, trying to erase here, not doing so well. So that forms the aldehyde. Now, there's 2 things that can happen at this point. The aldehyde is going to be a vapor, so you could just let the aldehyde escape, although I assume you're making the aldehyde for a reason. So you could allow this vapor to continue over through what we call a condensing tube and let it condense back into a liquid and collect it in a separate container as an aldehyde. Or you can keep this vapor from escaping and again let it liquefy or condense, but as it liquefies, have it drop back into the reaction vessel, and then it will continue to be heated with more of the oxidizing agent, more of the potassium dichromate or dichromate, whatever it is, and we call that reflux. If you think of acid reflux, people have heartburn, they have stomach acid comes up their esophagus, so reflux means like, to back up, to reflow through an area. So with the reflux, that aldehyde will get oxidized again, and when that happens, we end up with the carboxylic acid. And this whole process works because the nonpolar aldehyde is going to have a much lower boiling point, and it's going to naturally boil off of the solution as the primary alcohol is oxidized into that aldehyde. So let's look at the second reaction. Once you have the aldehyde, remember my aldehyde has a hydrogen, and it's got the double bonded oxygen, and then it's got the rest of the backbone, whatever alcohol this would happen to be. And as we add more oxygen, what happens is a second oxygen gets added right here to transform this hydrogen into an OH group. And now I have a carboxylic acid. And again, the dichromate is generally shown as plus concentrated oxygen along with heat as being the reagent. If you're going to continue to collect the aldehyde and heat it further, then we usually indicate that with the reflux up here. But you notice the conditions of the reaction are given with the arrow sign to make it clear how this is happening. So you need to mention these conditions when you talk about oxidizing a primary alcohol or oxidizing any alcohol. So primary alcohols have 2 potential products, an aldehyde or a carboxylic acid. And if you think about it, that should make sense that those 2 products have to form from a primary alcohol because both an aldehyde and a carboxylic acid functional group have to be on an N carbon. So here's a couple pictures that maybe will help clarify the difference between collecting the aldehyde and refluxing the aldehyde to produce carboxylic acids. Both setups are similar. You've got your flask there that you're heating it up in. We've got 2 different kinds of flasks that are being heated, but in both flasks you have the alcohol. The one on the right, you see that it's orange. That's the dichromate in there. Being orange, when this is completely converted to carboxylic acid, that will be green instead, so I will know my reaction is complete. But in each case, I've got this long tube that the aldehyde is going to vaporize into with its low boiling point. And then in this tube, as it comes across, cool water is being run through. That's what these tubes are showing, is they're running cold water through. So the aldehyde is going to cool back down into a liquid, and the liquid aldehyde is going to drip down into this container and be collected as an aldehyde. But in this tube, it refluxes up, and the assumption is that by the time it gets up to the top or before it reaches the top, it is going to have cooled down back into droplets, and those droplets are going to drop back down into the reaction vessel or be refluxed and then continue to be oxidized into carboxylic acid. So what happens if it's a secondary alcohol? Well, it's basically the same thing. You're going to heat it with the dichromate. You're going to allow it to reflux. So it's going to look like the second apparatus there. And now the same process is going to happen, that you're going to lose the hydrogen from the hydroxyl group, and you're going to lose this hydrogen. So now what you're going to have left is you're going to have a carbon with the double bonded oxygen with the CH3 group on each side. So now you've got a ketone instead of an aldehyde because the OH group was on an inner carbon. And if you continue to heat this, that can't oxidize any further. There's not a hydrogen here for an oxygen to come back in. So we can't suddenly have a COO group in there to form an ester. That won't happen. There's not a hydrogen for that to happen. So very similar. And again, if you think about it, an inner carbon could pick up an oxygen to become a ketone. So hopefully these three products make sense. So then what happens with a tertiary alcohol? Nothing. There is no hydrogen for the oxygen to bump off. So you would have to actually bump off a carbon, which requires a lot more energy. So this is not going to easily happen. So in general, tertiary alcohols are considered to be, are not easily able to be oxidized, and we don't even worry about what that mechanism would look like because it's so much easier to oxidize a primary or secondary alcohol. And so there'll be no color change if you try to oxidize a tertiary alcohol. So to sum up here, a primary alcohol can be oxidized to an aldehyde and or a carboxylic acid, and you will see your acidified potassium dichromate change from orange to green. A secondary alcohol will be acidified to a ketone, and again the color changed from orange to green. But the tertiary alcohol will not easily be oxidized, so there'll be no color change. Then one last reaction that alcohols commonly undergo is called esterification. So remember, an ester is when you have the COO group between two carbon groups. So it's a carboxylic acid that's had its hydrogen group at the end of the COO, at the end of the functional group. So this hydrogen gets replaced by a carbon group. So how does that happen? Well, what actually happens is the whole OH group breaks off. At the same time, a hydrogen group is broken off of an alcohol, and that forms an H2O, so it's sometimes called a condensation reaction. And now the carboxylic acid and the alcohol backbones merge together to form your new ester. So here's my original carboxylic acid. Here's my original alcohol, and I name it ethyl ethanoate. So I name the I named the alcohol first, the ethyl, and then I named what was donated by the carboxylic acid. In this case, they're both ethyl groups, so it's going to be ethyl ethanoate. So what's the significance of esters, and why do we bother making them from alcohols? And just a quick note, the resulting ester is going to have a lower boiling point than the more polar carboxylic acid or alcohol because they both have hydrogen bonds. So we can also collect an ester by distillation because it will boil off before either the alcohol or the carboxylic acid. It's also a reversible reaction, so we do use a catalyst, concentrated sulfuric acid, to drive the reaction to the right to produce this ester. And it's used like the esterification of salicylic acid is used to make aspirin. It makes it more tolerable to the human body. Believe it or not, it actually makes it taste better. If you've ever tasted aspirin, it tastes really nasty. Morphine can undergo esterification to form heroin, which generally isn't considered a good thing because it makes heroin much more potent and actually makes it far more dangerous for the same reason, because now being nonpolar or much more nonpolar, it can cross what we call the blood-brain barrier, Most things cannot easily get into the brain because there's a fatty protective layer around it, so only nonpolar things are able to transfer across or move across that blood-brain barrier. So the nonpolar heroin gets into your brain much more easily than the morphine. On a more positive note, esters are known for their pleasant smell, so they're commonly used as flavorings and in perfumes, but they're also used to make various painkillers. They're used as solvents for paints, varnish, that type of thing. And they also make up important biochemicals like the fats and oils in our bodies, along with important part of the DNA and RNA molecules.